No.
In that situation with the good split artery, I mean, it's gonna.
I'm in the orders. I'm feeling a lot better about it now.
I would give me like probably a positive on that too.
We're going to go ahead and get started. So, good morning, everyone. It's my pleasure to introduce today's speaker, Dr. Max Meneveau. Max was born in Baltimore to parents who immigrated from Chile. He pursued his undergraduate studies at Cornell, where he discovered his passion for medicine. Balancing his academic pursuits with his love for the outdoors, he spent his summers as a fly fishing guide and instructor. He then attended medical school at UVA, as we all know, where his interest in surgery began. He was fortunate to match at UVA for his general surgery residency, where he quickly discovered his interest in breast surgical oncology. During his time in the lab, he achieved a master's in clinical research and was notably productive in publishing research with his mentors, Dr. Showalter and Dr. Slinghoff. Next year, he'll be heading to New York City for a fellowship at Memorial Sloan Kettering. And of course, his journey and accomplishments would not have been possible without the incredible support of his wife, Nicole, who is here with us today. This year, their family grew significantly with the birth of their twins, Nora and David. Please join me in welcoming my very good friend, Dr. Max Meneveau, for his grand rounds titled Healthcare AI. It'll be pretty good, but we should curb our enthusiasm.
So what Ziad didn't say there is that that introduction was written by ChatGPT. So I have no financial disclosures, but parts of this talk were written with assistance from artificial intelligence. 3.5 years ago, in early December of 2020, the pandemic was raging. The vaccine rollout was just beginning, and there was a lot going on around the world. I was sitting at my desk working from home. I remember this very clearly. I was scrolling through Twitter, and I stumbled across an article that fundamentally changed the way that I think about science and the future of how we practice medicine. I initially thought this was clickbait. This is what the tweet said. The game has changed, AI triumphs at protein folding. I thought, well, okay, this is wildly overblown and probably fake news, but I clicked on the link anyway, and I read the article. How many of you have heard of the protein folding problem? A couple of you, probably because I mentioned it to you. I first heard of this concept during my biochemistry course as an undergraduate student. It was close to the end of the semester, and the professor put up a slide with the greatest unanswered questions in biology. The origin of life, what caused the Cambrian explosion, the evolution of the human brain, and the protein folding problem. The professor told us about how a biochemist named Christian Anfinsen in 1972 proposed that being able to predict a protein's three-dimensional structure just from its amino acid sequence was theoretically possible, and that it would revolutionize biology and medicine sometime in the future. This protein folding problem has since been considered one of the most important unsolved issues of modern science, and has stood as a grand challenge in the field of biology for over half a century. My professor gave us a very passionate lecture about this challenge. He spoke about how this problem is unimaginably complex. The total number of possible conformations of an average protein is 10 to the power 300. That's more possibilities than the number of protons in the known universe. In the middle of this really passionate description, a hand shot up in the front row. It was one of my fellow pre-meds who was furiously scribbling notes. And without looking up, he asked if this was going to appear on the final exam. I have to admit, I totally forgot about this lecture, and thankfully it didn't come up on the final. But the memory came back to me as I was sitting in my room working, reading this article. And the article essentially said that this problem had been solved. What the article describes is an AI algorithm called AlphaFold, which has successfully predicted the 3D structure of many, many proteins with the same degree of accuracy as the traditional experimental methods. To date, AlphaFold stands as arguably the most significant contribution of artificial intelligence to science. But why is this such a feat? And what does it tell us about the capabilities of artificial intelligence? So bear with me for a few minutes. We're going to get a little in the weeds, but I promise we'll make it through, and I think it will highlight how tough this challenge really is and how amazing the algorithm that solved it is. Before 2020, the only way to determine the 3D structure of proteins was through painstaking experimental methods like X-ray crystallography and nuclear magnetic resonance spectroscopy. These experiments, they often take years to complete, and the joke among biochemists is that it takes a PhD student their entire PhD just to solve the structure of one protein. Because this is so cumbersome, the structures, being able to identify the structures quickly is very appealing. So in 1990, there had been significant improvements in computing. So it became clear that computers would be critical to being able to solve this challenge. A group of structural biologists led by John Malt at the University of Maryland started a competition that was held every 2 years to test computational models for protein structure prediction, essentially the Olympics for structural biologists. What they did was to convince research groups around the world to hold back and not publish a few of their experimentally determined structures each year. This created a database of publicly unknown 3D structures for computational biologists to test their predictive models on. This worldwide competition was called the Critical Assessment of Structure Prediction, or CASP. Every 2 years, the biologists would test their models during this competition. And every single time, honestly, it did not go very well. So here's the results from the competition year by year. And as you can see, it's pretty bad. Basically, the best teams were only achieving about 40 to 50% accuracy. During the 2018 competition, there was a little bit of an improvement with a group named DeepMind from Google submitting an algorithm, which was called AlphaFold, which slightly improved the accuracy to 55%. In 2020, though, the same group, Google DeepMind, submitted an improved model named AlphaFold 2. This model can predict most structures as accurately as the gold standard experimental method, somewhere around 90%. So this is really an incredible achievement, and some have now considered the protein folding problem to be solved. In the years since, DeepMind has predicted and made public the 3D structures of every single amino acid sequence in the UniProt database. This represents nearly 500,000 proteins. This is the diagram of the algorithm structure. It's a series of interconnected neural networks, which ultimately lead to the predicted protein structure. And I know what you're thinking. Oh, geez, he's going to go through this whole thing and I'm going to fall asleep. Don't worry, I'm not going to go there. But the reason I show it is that it really highlights how complex the system is. It represents many years of work from biologists, computer scientists, physicists, and chemists. And as I've previously said, AlphaFold is the most significant contribution of artificial intelligence to science. It's a striking example of the way that AI can contribute to solving fundamental problems that face biology and medicine today. I think it's important to note, though, that this is a highly accurate system which was built for a very specific task, to predict protein structures. AlphaFold is an example of narrow AI. A lot of the current hype about AI is related to general artificial intelligence, essentially the idea that a single system could become intelligent in a general sense and be able to do tasks efficiently and with the flexibility of a human being. So far, the system does not exist yet. It's a goal of the field, but truly we're very far from having something that is successful like this. So in case you hadn't noticed, and I've mentioned it already, there's a really huge hype about AI. There's tremendous optimism about its potential, and some people even think that jobs are about to be replaced by general intelligent AI any day. Well, I believe these expectations are very, very overblown. While AI most certainly will change a lot about our lives, we need to be realistic about what computer models can actually achieve. So I thought I'd spend the next 30 or 40 minutes sharing how some of this AI works, some examples of how it's being implemented in medicine, and also want to address some of the fundamental challenges posed by the use of AI in taking care of our patients. So to start, artificial intelligence is the simulation of human intelligence in machines that are programmed to think and act like humans, essentially programming computers to perform tasks in a way that mimics how we do them. There are two main subcategories of artificial intelligence. The first and earliest is rule-based AI, which uses knowledge about a specific domain and a set of rules designed by human experts in that domain to solve problems. For example, clinical decision support tools are often based on expert systems. The second subcategory is machine learning. In machine learning, algorithms help computers learn from data in a task-designated fashion. The system is flexible and highly effective since computers can learn from new data rather than relying on previously generated human knowledge. Artificial intelligence is not a new concept. The idea that machines could be programmed to think and learn began in the 1950s with the mathematician Alan Turing, who theorized that machines could someday be able to think and be intelligent. He published Computer Machinery and Intelligence, a paper which proposed a test of machine intelligence called the imitation game. At the time, computer scientists were learning to represent logic within computers, which generated significant optimism that computers could soon be as intelligent as people. When the limitations of computing power overcame this optimism, it led to something called the first AI winter. This was a period of skepticism and disillusionment about artificial intelligence. From the 1970s to 80s, the refinement and development of computer technology created another wave of excitement about artificial intelligence. This was largely due to some of the success of expert systems. Some of the earliest applications of this was actually in healthcare. One of these expert systems was called Mycin, which was designed to provide antibiotic recommendations based on patient features. It was very successful, actually as accurate as the Stanford infectious disease faculty. But the system was never actually clinically implemented because of the huge computing power required to run the system and the lack of these resources at most hospitals at this time. During the 80s, expert systems were used at many banks and airlines to assist with decision-making, but the hype about their potential was not realized. In large part, this was because designing and implementing these systems was so resource-intensive, and every time new knowledge was gained within a specific domain, the entire algorithm had to be rebuilt. This led to the second AI winter, in which research and funding for AI dramatically decreased because of the failures of expert systems. Despite the lack of enthusiasm for AI, there were some strides forward during this time. In 1997, IBM released Deep Blue, the first computer chess program to beat the chess grandmaster. In the same year, a small company partnering with Microsoft released a highly accurate speech recognition software for use in healthcare settings. That company was called Dragon Systems, which many of you know is still used today for dictation of medical notes. So while these systems are not AI in the way that we know it today, they do represent steps forward in the way computers interact with and interpret human behavior and language, a key component of AI. Throughout the winter of the 1990s, a few mathematicians and computer scientists were still pushing forward and developing new ideas based on systems that were inspired by the human brain. Two key advances during the 80s ultimately gave birth to what we know as today as deep learning and formed the basis for developments like ChatGPT and AlphaFold. The first was the refinement of multi-layered neural network computing systems, and the second was an algorithm called backpropagation with gradient descent. This is what allows neural networks to learn from data and to continuously refine their predictive power. So now that we know some history of artificial intelligence, I want to explain a little bit about how it works. I'll focus on the machine learning side of AI since expert systems are a little outdated and have had their limitations. So here's the three main types of machine learning. Supervised machine learning involves training algorithms on labeled data sets, which means that each training example is paired with an output label. The goal is for the model to learn the mapping from the inputs to the outputs so that it can predict the label for new, unseen data. Supervised learning tasks are typically divided into two categories, classification and regression. This is used mainly where predicting outcomes or categorizing data points is essential. Unsupervised machine learning refers to a type of algorithm that is used to analyze and cluster unlabeled data sets. These algorithms discover hidden patterns or intrinsic structures in the data without the need for human intervention. And last but not least, reinforcement learning. This type of machine learning is where an agent learns to make decisions by performing actions in an environment to maximize cumulative rewards. Unlike supervised learning, which learns from data set and labeled examples, reinforcement learning is based on the agent's interaction with the environment. This type of learning can be used in various domains, such as robotics, gaming, autonomous driving, and recommendation systems. The major advances recently in AI have come from massive supervised learning models combined with aspects of unsupervised and reinforcement machine learning. So then what is actually a neural network? A neural network is a computational model inspired by the way that the human brain processes information. It consists of layers of interconnected nodes, or neurons, where each connection has an associated weight. The network is structured in different layers of nodes. The input layer is the first set of nodes that receives the input data. Each node in this layer represents a feature from the input data. The hidden layers are the intermediate layers between the input and the output. This is where most of the predictive power from neural networks arises, the math happening within each node. The final layer produces the output of the network, which essentially represents a prediction based on input data. Don't be too afraid. I mentioned that the nodes are connected to each other by weights and that some math happens within each node. The math happening is as follows. A weighted sum of all the prior node values is calculated. A bias is added to the weighted sum, and that value is then fed into what's called an activation function, which induces nonlinearity. This value is then passed to the next node, multiplied by the weight, and the next weighted sum is calculated. So at the end of all of these calculations, each node in the output layer assumes a value which represents a prediction. It could be the cost of gas given current market conditions, the blood pressure based on ICU data, and so forth. This is really great. We can input some values and generate a prediction after doing some math. But some of you are probably wondering, where do we get the value for those weights and biases? Well, this is actually where the magic happens, and it's the essence of how the model learns. The weights and the biases are generated during the training phase, building the model. So to explain this, I think it's best to use an example. Let's address an important question that can impact a lot of people. Imagine for a few minutes that you're Dr. Friel, and you want to build a neural network that will predict if a resident is going to need parental leave or not next year. This would be very useful for him in the scheduling chiefs. So you have a data set that includes all prior residents in the program and variables associated with them, such as their age, their average duty hours, their ABSCIIT score, and whether or not they need parental leave. The first step is to train the network with some of our data and then test how accurate the network is using the rest of our data. So the first step is to split the data set into two parts. Since training requires a lot of data, it will need to be an unequal split, where 85% of the residents are randomly assigned to the training data set and 15% to the testing data set. So now it's time to train the network. Data from each resident in the training set is passed through the network one resident at a time. For the first resident, the weights connecting each node are randomly generated. The data moves forward through the layers of the weighted sums are generated within each node until finally the data reaches the output layer. In this case, the network predicted that the resident will not be taking parental leave. All right, so the next step is to compare the prediction of the network to the ground truth, since we know whether that resident needed parental leave or not. But unfortunately, the network predicted wrong. In reality, the resident whose data was sent through the network did take parental leave. So here's where the key is for the learning. The information about this prediction error is passed backward through the network by something called backpropagation. Knowledge of the error allows the network to adjust the weights and biases based on the degree to which that particular value affected the incorrect prediction. This happens over and over again for each resident in the data set, with the weights and biases being adjusted until they reach a minimum contribution to the error. At this point, the network is considered fully trained, since the weights and biases can't be improved any further. There's some interesting math in this process. It's called stochastic gradient descent, but I'm not going to bore you with that. So now that the network's fully trained, its predictive power is then tested on the testing data set that he split off earlier. So hopefully it's accurate. So now that we have some background about how this all works, how can we apply it to healthcare? Probably the most successful healthcare-related AI models have been in image interpretation. It's relatively easy for computers to digest image information, so radiology and pathology have been obvious starting points for applying AI in healthcare. The most impactful application for AI in radiology is in limiting the burden of reading very frequently performed studies, most of which are normal. So significant efforts have been made in mammography, for example, to develop AI that can detect breast cancers as accurately as human radiologists and be accurate in detecting if a study is normal or not. The hope here is that these models could help triage mammograms in order to deprioritize high-confidence normal studies. A number of models using deep learning networks have been quite successful at this, with one study showing that human radiologists plus an AI was just as accurate as two radiologists reading the same film. Another study, which used a model which was trained on 200,000 mammograms, showed that an AI was highly accurate for identifying normal mammograms and significantly reduced the workload for radiologists. So here's a very relevant example for us. Like I said before, machine learning is very good at imaging analysis. With laparoscopy and robotic surgery, we're constantly looking at our patient's anatomy through a digital lens. Images can therefore be interpreted by AI in real time and make suggestions or highlight areas of interest. This is exactly what a multi-institutional group has tried to do for cholecystectomy. This is not yet integrated into clinical use, but the group has shown that deep learning networks can successfully annotate videos of laparoscopic cholecystectomy, demonstrating safe and dangerous zones of dissection. I'll just show this video briefly. So beyond image analysis, large language models like ChatGPT will also significantly affect our work. In the fall of 2022, when ChatGPT went viral, I think we were all pretty amazed and honestly kind of freaked out by it. It was the first time that most people had interacted knowingly with a highly developed artificial intelligence system. I remember my dad's reaction when I showed him how ChatGPT could write him a fairy tale. He was very unimpressed. He said it seemed a little gimmicky, but he's an engineer. I then explained that it was a very flexible system and it could do a lot of things. So, and I quote here, he asked it to write a Fortran program for direct numerical simulation of isotropic turbulence. Apparently this is a very difficult problem, and ChatGPT started responding, and my dad was honestly shocked. The AI actually did most of it correctly. He told me it performed almost as well as his graduate students. So while AlphaFold is the most significant scientific contribution of AI, I believe that large language models like ChatGPT represent the most significant contribution of AI to our day-to-day work so far. These models will fundamentally alter how we document our work and what we spend our time doing. Earlier this year, the Permanente Medical Group published a paper describing a pilot trial of an AI scribe for clinic note documentation. Over 3,000 physicians were part of the study, and this included over 300,000 patient encounters. The AI scribe was designed to listen to the visit and generate H&P or progress notes based on the encounter. The system was highly rated by both patients and physicians and was found to be accurate and to decrease the overall burden of notes. On the right side here are the figures from this paper. Higher numbers represent a greater decrease in the time spent on certain tasks when the AI scribe was used. So most notably, the time spent in electronic health record related activities outside of usual work hours was significantly lower when the AI was used. And the time spent writing notes during the clinic appointment itself was also much lower. As these systems get better and better, they will eventually be fully integrated into the electronic health record and form the basis for how we document our visits. So I mentioned earlier that deep neural networks require a lot of data. For scale, the network that built ChatGPT uses over 170 billion internal parameters and was trained on 45 terabytes worth of text data. That's over 3.7 billion pages of text. Thankfully, there are plenty of highly accurate models that use for healthcare that don't use nearly this much data. But the scarcity of labeled medical data is a real problem. Having enough labeled data is critical for training deep neural networks, but there are significant barriers to obtaining this, such as the time required to label the data, the costs, and difficulties with data privacy. So what can we do when our question requires a lot of data, but we don't have enough? So let's get back to our example of Dr. Friel's neural network. Clearly, something went very wrong this year because this was not predicted, the amount of parental leave that was taken. So how can we improve this network? His network probably didn't have enough residents in it. So his database was just way too small. One thing he could do is to use generative AI technologies to increase the size of the data set. I know this makes a lot of you very uncomfortable. How can we just invent new data? This cannot possibly be a good idea. But surprisingly enough, this actually does work. Generative AI models can digest a small data set, learn the internal statistical relationships within the data, and generate fake data that preserves the structure of the original, but is 100% synthetic and not the same as the original. So how does this work? Well, there's a number of methods for generating synthetic data, but by far the most well-studied is called a generative adversarial network, or GAN. You can imagine a GAN as a game or a boxing match between two neural networks, a generator network that learns to make fake data from random noise, and a discriminator network that learns to determine the difference between real or fake data. Throughout the training of the GAN, the generator will create synthetic data, which is shown to the discriminator along with real data. The discriminator then has to make a choice of whether the data it is seeing is real or synthetic. If the discriminator wins the match and correctly identifies the data as fake, this information is passed to the generator, which updates its internal parameters and improves itself. Similarly, if the discriminator loses the match and makes an incorrect judgment, its own internal parameters are adjusted to make itself perform better. Eventually, as the game is played, the generator will have learned the statistical distributions within the real data so well that it can generate indistinguishable data from the original. So this is incredibly useful. Dr. Friel can massively increase the size of his resident data set and now train the neural network. He can then use that synthetic data for the training, and assuming that his network is reflective of reality, it should be very accurate when tested in the real set. Synthetic medical images are extremely useful when developing classification models for automated reading of chest x-rays. Some of the diseases or conditions that one would want to diagnose are very rare, which poses a challenge when developing deep learning models. When data sets are imbalanced for rare diseases or findings, the diagnostic models can become biased and perform very poorly. So one way to overcome this is to generate synthetic images containing the rare finding so that the data set becomes more balanced. So I just want to do a quick demonstration of how good these images have become. So I have two pictures here, two chest x-rays. Can you guys tell the difference between the real one and the fake one? Anybody want to vote for A or B? A? No. B? They're actually both fake. How about here? Someone has a pleural effusion, there's a real one. This one actually does have a fake one and a real one. this one's fake. So these things have gotten really, really accurate. But it's not only used in chest x-rays. It's gotten accurate for pathology slides as well. This is a panel from a paper in Nature that describes an algorithm which uses something called diffusion methods to generate very realistic looking normal and abnormal histopathology slides. These are all synthetic. The same paper also shows this for images of dermatologic conditions, also all synthetic images. So I've shown you how realistic this fake imaging data can be, and that it's useful for situations where we want to train deep learning models, but don't have enough data, or situations where there's imbalance in the data set. Another way in which synthetic data can be used is with security and privacy. Some very interesting work is being done on electronic medical records for improving healthcare system efficiency and patient flow through the hospital. A large barrier to this is HIPAA. You can imagine that hospitals are definitely not going to share their entire EMR worth of data because it's identifiable. So one way to address this is by generating a synthetic copy of the entire EMR, which can then be freely shared because it is in no way identifiable. This will likely be the most impactful way in which synthetic medical data is used. So I've shown a few interesting examples of how AI is being used, and honestly, what's being achieved by generative AI these days is truly incredible. I haven't even really touched on ChatGPT that much, which if you haven't seen, just recently released an interactive version where you can talk to it and it talks back in a very eerily realistic way. So with all this progress, it would be very easy to fall into the current hype and develop unrealistic expectations of what AI can actually achieve. Don't get me wrong, this is fundamentally changing the way that we live our lives, but much of the current hype is overblown. There remain truly significant challenges facing AI. And I think it's important to recognize these challenges so that we don't plunge into a third AI winter when inflated expectations are not met. We still haven't truly seen AI models make the transition into widespread clinical use, for the most part. Some have, but by and large, despite the insane amount of models that are being published in journals and being developed by companies, there has been a lack of widespread adoption. Why could this be? So first, there's a huge cost of implementation. And since these things are so new, health systems have been hesitant to pay for something that's relatively unproven. Also, there's no established way that payers can reimburse health systems or practices for the use of AI in delivering health services. There's ethical concerns. So what happens when an AI is wrong and a diagnosis is missed? Is the developer liable or the party that uses it? And most importantly, there remain significant problems with model generalizability. This is the phenomenon where highly accurate models in an academic setting struggle when they're applied to the real world, where the populations may not be similar to the training data. This is a famous cartoon in the machine learning community. It captures very well that last point that I made. The data distribution in the training of an algorithm needs to be representative of the population where that model is being used. Otherwise, the model is useless when it's applied in the real world. One of the most striking examples of this happened during a clinical trial which was done in Thailand. A group from Google Health created a deep learning system to diagnose diabetic retinopathy. It was highly accurate in the training phase and in the testing data set. But when it was applied in practice, the algorithm failed to work at all on more than a quarter of the patients and added significant delays to their clinic visits. The project was a failure in practice because the images obtained from the clinics all had significantly different lighting situations compared to the images from the training data. So at the end of this paper, the authors conclude that for system developers, this means that formative research which provides a strong understanding of clinical users and their context is critically important to the success of such a system. A common saying in data science is garbage in, garbage out. The very best models depend completely on the quality of the data that's used to train them. As I mentioned earlier, bias is a barrier to good machine learning models. In a way, this is because bias in the training data limits generalizability. But another way in which bias can be bad is that machine learning models can amplify the biases within the data and lead to more social inequality if applied on a large scale. This is a really very interesting study that examined the biases that can be amplified when machine learning is used in job recruitment. One of the things that job recruiters do is send targeted ads to people who they believe will be good candidates for the job. In order to do this effectively, and at a large scale, they use AI to identify people in occupations that match what they are looking for. It turns out that it can be very hard to identify someone's current occupation, even from their LinkedIn profile or webpage. So what the AI does is it determines the occupation based on a person's biography, which is often available on the web. The study here sought to determine whether the AI was accurate in predicting someone's occupation if they were in a job that had historically high gender imbalance. So the data set they used had some surgeons in it, and about 14.6% of those surgeons were female. They then wanted to see whether this widely used recruitment algorithm could accurately identify the females who were surgeons. And they found that among surgeons identified by the algorithm, only 11.6% were female. So that's a significantly lower estimated rate than the reality. And so an already established bias got augmented by the algorithm. And you can imagine that this would have tremendous real-world consequences. If this recruitment tool is being used, and it actually is being used, then fewer women will be identified among the possible candidates for these jobs. And finally, I also want to highlight that a lot of the algorithms that are being used and developed for deep learning are what we call black boxes. In truth, we don't completely understand why they predict the things the way they do, because the interconnected relationships within hidden layers of the network are too complex for the human mind to understand. This can generate a lot of mistrust and skepticism among users, and especially for physicians. We thrive on understanding why things are the way they are, and these models often do not make that possible. So despite the limitations and challenges I just discussed, and by the way, that's not at all an exhaustive list of the issues, AI is going to change the way that we do medicine and surgery. It will have applications in clinical practice, in biomedical research, public health, medical education, and health administration. Just look at how much has changed since the widespread adoption of the personal computer. AI, like the PC, is a transformational technology. It will touch all aspects of life in some way or another. But one constant in all of this change is that we are humans who care for other humans, and that is not something that can be replaced. There's a fantastic book titled Deep Medicine by Eric Topol. In this book, he describes how artificial intelligence is helping bring the humanity back to healthcare. In finishing this talk, I want to read an excerpt from this book because it really captures well what lies ahead for us as physicians entering the AI age. So he says, AI is going to profoundly change medicine. That does not necessarily mean for the better. The applications of the technology may be narrow and specialized today, with many of its benefits still in the promissory stage. But eventually, it will affect how everyone in medicine, not just pattern doctors like radiologists, pathologists, and dermatologists, but every type of doctor, nurse, physician assistant, pharmacist, physical therapist, palliative care provider, and paramedic does their job. We will see a marked improvement in productivity and efficiency, not just for the people, but for operations throughout hospitals and clinics. It will take many years for all of this to be actualized, but ultimately it should be regarded as the most extensive transformation in the history of medicine. The super streamlined workflow that lies ahead of us, affecting every aspect of healthcare, how we know it today, in one way or another, could be used in two different ways. To make things much better or far worse. We have to get out in front of it now to be sure this goes in the right direction. So if I leave you with one last thing today, I hope that I have inspired you to be thoughtful about how artificial intelligence is impacting us and to be hopeful about the future of medicine. What will you do to make sure this goes in the right direction? So for the last 11 years here at UVA, I've had the incredible fortune of having you all as teachers, friends, co-residents. While I may not have individual photos of everyone, please know that you've all played a crucial role in my development and that I could not be more grateful. I want to express my heartfelt thanks to my mentors, whose guidance and wisdom have been invaluable. Thank you especially for pushing me to do better, for inspiring me, and for supporting my path. I'd like to thank my parents and sister, but most importantly, none of this would have been remotely possible without the unwavering support and patience of my incredible wife, Nicole. Thank you all so very much.
What percent of that was AI generated?
The pictures and the definition of AI.
So Max, that was the conclusion of a great series of presentations by all of our chief residents. So, I want to thank you for, I don't know how many years it's been now, but I mean, it's 7+, right? 11, 12, something like that.
11 years.
Yeah. So, I mean, I was a young man when you started, now I'm an old man. So, but it really does highlight like your intellectual kind of approach to the whole process. I mean, not just this particular one, but how you kind of have thought about residency and life and all of that. I'm looking forward to my neural network that will help me predict parental leave. So I have a couple questions for you. One is, at least, like, there is a fear of this, right? And so even at the APDS, I think we're making a recommendation that says you cannot use AI for letters of recommendation or whatever, which seems a little too much to the one extreme. The other thing, because I actually wrote a letter recently using AI after we talked to see how I could use it. It did not save me any time whatsoever. Now, part of that might have been that I was just learning how to use it, but perhaps what we need to do now, and maybe comments, is a little less of we can't use it, as opposed to how maybe we should teach people how to use it wisely, and how to effectively do it. So I just love your thoughts about the fear and how we can implement this in some sort of way, because it is going to happen. It's just, to deny it is just be ridiculous.
Yeah, so that's a great question. To address the fear part, I think a lot of it has to do with not understanding how it works and not understanding the theory behind it. And so that requires education and people actually spending the time to learn a little bit about how these things work. And I do think that we're going to all have to learn how to use it appropriately. I think this will eventually, there have to be some curriculum or something that people learn how an appropriate use of ChatGPT, for example, is to write a paper. So when I write stuff with it, I use it as a starting point, and I use it to inspire ideas or to fix language that's difficult, but I don't use it to come up with something that I don't personally believe.
Max, that was excellent. Thank you. I was struck by how much of the healthcare research progress in AI has been done by these industries, right? The Google, IBM, Microsoft examples that you gave. So as we look towards the next phase and developing excellent tools for research or actually delivering healthcare, how do you see academia versus industry working on that?
That's a very good question. I think that a lot of this has been pushed forward by those big companies because they have access to data. I mean, they have access to all the data, basically. And so looking forward, I think there's going to have to be real concerted efforts by academia to develop databases that are robust, but also large and shareable. And so one of those ways is the synthetic data, but I'm curious to hear your all's thoughts about how you see that. But yeah, really having larger data sets that are shared among institutions will have to be the future, unless we want Google and Amazon to control everything.
Max, beautiful work, and thanks for all you've been doing here for all these years. We look forward to your great future. You and I talked a little bit. You've shared your thoughts about what you may do going forward, but can you share a little bit of that about how you are thinking about this kind of work impacting your research career going forward?
Yeah. So I'm very interested in the idea that we can create essentially totally personalized care, and AI will certainly play a role in that. And so developing models that can predict outcome or response to therapy based on genomic features, clinical features, those are the areas that I'm most interested in. Anthony?
So when you think about like the surgeon scientists 10, 20 years from now and like where this technology is heading, how do you think is the best way for, surgeon scientists now to gather these skills, especially thinking about UVA that has, 2 T32 grants?
Yeah. So in terms of skill building and gathering, I'll be very honest. Most of what I know comes from YouTube and reading things online, and there's great EDX courses that cover this material. There's certainly a barrier to people right now who don't necessarily have coding backgrounds or computing, but a lot of the concepts are very transferable, and you don't need to know coding to understand the theory behind how this works. And so just understanding a little bit about the theory and appropriate applications can really open up doors. The other thing is collaborating. So, we as physicians have access to patients and their data. We have access to all the things that we want to know about how we do our job, like guidelines and things like that. So we have questions that we can then bring to people that are coders and the machine learning experts to bridge the gap between them and the clinic, basically. Dr. Sherman.
Max, that was really excellent. That's the most cogent talk I've ever heard on AI, and I've read some articles that are pretty confusing, but your talk was really pretty clear. It was great. And I think it just reflects the fact that you have a great approach, an intelligent approach to all the problems you've solved, both clinically and in your research work. So congratulations. My thought has wandered to the sort of sticky point you brought up about the finances. And that's going to be, obviously, the implementation is going to be different. Do you think there's any way that AI can be used to help solve the cost crisis in healthcare?
I think that's one of the most, probably the best way to use AI. It's going to be really changing how we make decisions. And so as decisions become more streamlined using AI, we're going to have a lot less medical waste. So doing studies that are not going to change the way we do what we do with a patient, for example, I think AI will be able to recommend studies that are more appropriate. And so we'll have less medical waste in that sense. But that's going to take a lot of work, and it'll take a lot of convincing whole health systems to change the way that they practice. So it's a very unclear future, but I think it's clear in the sense that that's where it's going. Just how we get there, that still is in the air.
Excellent talk, and I think we all would have had a predictive model in our mind that would have suggested you were going to give such an excellent talk based on your performance and everything you do. I think you, as a surgeon scientist, are ahead of your time. The strength we have here at UVA is incredible. Having our undergraduate disciplines in the same location as our medical center is something that is an absolute strength for us. And just thinking over the years, the collaborations I've had in my lab with some of the bioinformatics folks, they were using machine learning, and I didn't even know that's, random forests and all of the processes they were using to analyze genomic data from our lab. I didn't even realize it was machine learning and artificial intelligence. And the expertise, Chongzi Zhang and his whole group and everybody in public health sciences and the genomics center, it's incredible and something that we should tap into. Now, I think UVA's positioned to really become a national leader. The School of Data Science, the dean, is a world-renowned expert in neural networks. And so I think our ability to leverage the strengths in the School of Data Science and the folks in bioinformatics here will be a strength, and you are way ahead of the curve and ahead of your time. So kudos to you, and look forward to following your career, because I know you're going to be incredibly successful, and best of luck in that endeavor. So thank you.
Thank you. Dr. Bremen.
Well, Matt, I just want to congratulate you on an amazing talk, but also amazing performance as a resident in this research. It seems to me like artificial the use of AI could be very attractive to try to address inequities in healthcare. We have that is one of our biggest problems in the United States, that the haves and the have-nots, and in many states, the haves aren't really caring about what happens to the have-nots. So if we had a way to be able to offer care to people that really can't afford care, I think that would be one of the best uses for AI. Very complicated, of course, but AI hopefully will have a very big impact on societal issues in a positive way.
Yeah.
Great job.
Certainly. Thank you.
Well, Matt's another example, like you and your colleagues. I'm so proud of all of you guys. Not only you guys, excellent surgeons, compassionate doctors, and then you can just see your career is going in the future is going to continue with innovation, curiosity. I hope, I'm hopeful that all of you guys will continue to stay in academia and continue to be role models. Because as residents here, I mean, this is exactly, the type of, sort of chief resident that all of us as faculty are proud to be part of your training. Wish you best of luck. We can talk a little bit about your future career and stuff, but hopefully, it's something like, continues to be at UVA. So thanks a lot, Max.
Thank you all so much.